In this video, we will talk about polarization of light. Light, which is a type of EM wave, consists of fluctuating electric field and magnetic field that are perpendicular to each other and both individually perpendicular to the direction of propagation. Here, the vector c represents the velocity vector of the wave. We define the direction of polarization of light or of an electromagnetic wave to be the direction of the electric field and not the magnetic field. If the light is polarized, say along the y-axis, then the electric field vector would oscillate like that. Given that this is the y-axis, this arrow indicates the direction of propagation of wave, which in this case can be taken to be along the x-axis. If, for example, the electric field vector in this particular wave is oscillating along the z-axis, then we say that this light or this electromagnetic wave is polarized along the z-axis. So in general, the electric field vector can oscillate about any angle, as shown like that, or like that, and so on. Light with this sort of electric field vector oscillation are known as polarized light. If the E field or the electric field vector are oscillating in a following manner, like that, the oscillation is pretty much everywhere on this, let's say, YZ plane, with the direction of propagation of this electromagnetic wave for light is along this x-axis, then such a light is known as the unpolarized light. Polarization of light can be observed using an apparatus known as polarizer. A polarizer consists of a polarizing axis, say like that. So if an incident light is polarized in the same direction as the direction of that polarizing axis, like that, 100% of this incident light will be transmitted through the polarizer. So that means if the incident light has an intensity of I0, that transmitted light will also have an intensity I0, 100% transmission. However, if the incident light is polarized perpendicularly to the direction of that polarizing axis, there will be zero transmission on the other side. For any other intermediate cases, for example, such as this one, where the direction of polarization of that incident light is theta degrees with respect to the polarizing axis, the emerging light would have intensity according to the following expression: I0 cosine squared theta, where I0 is the original intensity, or the intensity of the incident light, I is the intensity of the emerging light, and theta is the angle between the original polarization direction and the polarization axis of that polarizer. This result is known as Malus' law. So it is clear that the emerging light will be polarized in the same direction as the direction of that polarizing axis of the polarizer. What happens if the incident light is an unpolarized light? Then according to this formula, the emerging light would have a following intensity. It is calculated as the average of the right-hand side expression. So I0 is a constant. The average of I0 is I0. The average of cosine squared theta taken over 0 to 2 pi radiant is half. So intensity of light that emerges is I0 over 2, half of the incident light intensity. Let's look quickly at this problem. The incident unpolarized light has intensity I0. Find the intensity transmitted by the first polarizer and the second if this is the second, if the angle between the axis of the two filters or the two polarizers is 30 degrees. So that is the polarizing axis of the first polarizer, that is the polarizing axis of the second polarizer, and the angle between them is 30 degrees. As this unpolarized light gets through the first polarizer, what is that intensity? Now we know this is an unpolarized light, so the intensity through the first polarizer must be half of the original intensity. If the original intensity is I0, then I1 is half I0. I1 will hit the second polarizer, and what comes out on the other side of the second polarizer is I2. So what is I2 in terms of I0? Using Malus' law, we know that I2 equals I1 cosine squared of the angle between the polarized direction of the light that is hitting polarizer 2 and the polarizing axis of the polarizer 2. So that means the angle is 30 degrees. Keep in mind what emerges from polarizer 1 is polarized in a direction dictated by the polarizing axis of polarizer 1. So that means I1 is I0 over 2. Since cosine 30 is square root 3 over 2, and you have to square that. So that means I2 over I0 is 3 over 8. So only 37.5% of the original incident light that gets out of the second polarizer. Let's look at this problem. You want to rotate the plane of polarization of a polarized light beam by 45 degrees with a maximum intensity reduction of 10%. How many sheets of perfect polarizers do you need to achieve your goal, and what is the angle between adjacent polarizers? So let's assume you have a few polarizers. This is polarizer 1, 2, 3, all the way up to n polarizers. So the angle between the first polarizer and the second polarizer's polarizing axis is theta. Likewise, the angle between the second polarizer and the third polarizer's polarizing axis is also theta, and this pattern continues all the way until the last polarizer. So the angle between the polarizing axis of the nth polarizer and n-1th polarizer is also theta. So let's assume that you have an incident light polarized like that with intensity I0. You want to bend this direction of polarization to that direction of polarization, and the angle between the first and the second polarizer's polarizing axis is 45 degrees. And the intensity that comes out over here is 0.9 I0. So a reduction of 10%. You want to determine theta and capital N. So let's write down an expression for I1, the intensity of light that transmitted through polarizer 1. Let's assume the angle between the polarizing axis and the direction of polarization is theta. So I1 is I0 cosine squared theta. Now let's write down I2, the transmission intensity through the second polarizer. I2 in terms of I1 is I1 cosine squared theta. Substituting the expression for I1 from here inside of that, we get I0 cosine to the power 4 theta. Now what comes out through the third is I3 equals I2 cosine squared theta. Using the expression for I2 from there, we get I3 to be I0 cosine to the power 6 theta, and so on. With such a trend, we see that what comes out through the nth polarizer is quite simply I0 cosine to the power 2 times n theta. But we know In is 0.9 I0 due to that 10% reduction. So substituting this in here, we get 0.9 equals cosine to the power 2n theta. We also know since there are n polarizers and each contributes an angle of theta towards bending the light to final 45 degrees, we get n times theta is 45 degrees in radian, namely pi over 4. Let's substitute theta from this expression in here, and you get that. Now all we have to do is to find the value of n that satisfies this equation. And you can start doing by substituting n equals to 1, 2, 3, and so on. And you will see when n is 6, this equation is satisfied to a good degree. So that means we need 6 sheets of perfect polarizers to achieve our goal. And the angle in between successive polarizers can be determined from that equation. So n now is 6, so theta is pi over 4 times 6. Remember, in degrees, pi is 180 degrees. So theta is 180 divided by 24, and that's going to give you 7.5 degrees. And that is what theta should be. And that solves the problem. Thank you for watching.